Before we get started with the next chapter, which will be chapter 4, I want to express some disappointment with the performance of students who have taken the first exam thus far. There were 3 students who did reasonably well, but there were several others who did very poorly. And while I don't know exactly why, each may be a separate case, but in case you're not using all the resources available to you, I wanted to emphasize at least one of them right now. So I'm in the course. I've gotten to the Brightspace course, and I'm going to show you where some useful practice is. Click on content. All right. And then you want to go, let's see, that's module 1. Let's go down to module 2, because that's where we're starting with today's lecture. Okay, over here in module 2, you've got your usual stuff. Here are the PowerPoints for chapter 4, okay, in 3 different flavors. And then these are old videos. You can look at those if you want, but there'll be a new one for this one today. Here's where I want you to learn these element symbols, and I made those available and showed you where they were at the very beginning. But now you need to learn those symbols in earnest. The next chapter 5, we'll get that chapter 5 on next Tuesday. And there's another lecture for chapter 5. Okay, now we get to review documents. This is a review document that looks that looks exactly like a paper exam, right? But most of you are not. Well, nobody's coming to class to take exams so far, so I assume that everybody's going to take them in Brightspace using Respondus Monitor and Lockdown Browser as the proctoring service. So if you want to maximize the time that you spend studying this material, you don't want to go to these review documents. Now, it's not a waste of your time, don't get me wrong, but if you're limited on time, go to these practice sessions that are available. Let's see. Let's move down. Yeah, that's not that good. Give me trouble here. There we go. You do have your homework. Here we go. Archive videos. Practice tests. Here we go. This is what you want to look for if you're going to take your exams in Brightspace. These practice exams look like what you'll see in Brightspace when you take the exam. So this would be a better place to spend your time if you're stretched for time. If you really want to learn chemistry, then you'll do all of it. But if you don't have the time available, then go to each one of these. Here's chapter 4. These are easy problems. So if you click on that, let's just do that one right there. These do not require Lockdown Browser or Respondus Monitor. So you go straight into them from here, and you can take them over and over and over again. Each time the system will grade it for you. So you'll see where your weak spots are. But I won't see those grades. So let's click on this one right here and see what it looks like. All right, so there are quiz details. Let me scroll down. There we go. And there we go. Start quiz right here at the bottom. So if you start this quiz, there you go. Now you got your questions and you can answer them. And when you submit that, the system will grade it for you and show you where you're weak. All right, so let's go back. If I can find the back button, it's right over here off screen somewhere. Okay, this is not working as well as I wanted to. I'm going to go to the computer and do it manually here. Once you're done, you would just hit that submit quiz, just like you were taking a real exam. Okay. And then after the warning, since I didn't put any answers in there, I got a warning on every question. And then it gives you your responses here. And actually, it gives you the correct answers, right? So you could see which ones you missed, plus what's the right answer. Then you want to go back in and take it again until you can get all the questions right. Okay, so let's go back. Here we go, and go back to content. And these practice tests are in several versions. Some of the modules will have easy, moderate, and difficult. Apparently, chapters 4 and 5 only have easy and moderate. Some of them are just pure memory. Some of them you have to work out problems. So you need to be diligent about the skills you need to work problems. And sometimes the best way to get those are to go to the review documents that I showed you earlier. Because along with the review document, there's a key and there's another document called worked problems. So I hand wrote how I answered each one of those questions and then created a PDF file out of it. So that's where you go if you don't understand why you got the question wrong. Go there and hopefully that will show you where you got it wrong. And if that still doesn't do it, come to me. All right. So if you use these resources, at least in the past, my students have been very successful drilling these quizzes. All right. So I think that's all I need to show you about that right now. Let's get to chapter 4. There it is. Okay. If you were coming in person, I'd have all the handouts that you can get in this module here, hard copy. PowerPoints are self-explanatory. The review documents we've already talked about. There are a couple other things that you might find useful. The periodic table, there's a periodic table in that module. Look for it. It says, know these. That's the one that has, and there's a slide on it here. I'll show you in a second. The ones that I want you to memorize are boxed in red boxes. So you memorize those. But you also have access to extra credits. And these are the only 2 extra credits that I give you this semester. And they are in this chapter. The first one is called Getting to Know the Periodic Table. So this is what the first page looks like, and these are instructions, right? How to do what I want you to do with this blank periodic table. There it is. Right? Tells you how to put the elements in there, what to put in there, how to identify them. It's self-explanatory. That's one extra credit exercise. The second extra credit exercise, that first one, of course, is for chapter 4. This one is for chapter 5. So I wouldn't try to do this one until you've covered chapter 5 and learn the rules for naming compounds. Once you know those rules, then you should be able to go in here and either write the compound formula from the name or write the name from the compound formula. There's a mixture in here of those 2 types, and your answers will go right here, right? 50 of them. If you need to know polyatomic ions, which we haven't covered yet, but you'll understand when you get there, here's the list of polyatomic ions, so you don't have to memorize them. You do have to memorize the symbols for the elements that I give you in that special periodic table that I'm going to show you again in just a second. The important thing is that these are extra credit. And together, these 2 count 1/2 of an exam grade. So you can build up quite a few points if you spend the time and submit these. Now, how do you submit them? Well, the naming compounds is in a PDF document that is fillable form. So you can fill it out, and in your Acrobat reader, you will be able to save your work and submit it that way. For this one, you're going to have to print this one off, do it by hand, and then scan it or photograph it and submit both the top page and your work page. I use the top page to grade. You know, I circle and add or subtract points from this, and then I calculate a grade at the bottom. So send me both of them with your names on both of them also. I don't want to have to guess who's doing the work. Okay, so let's get to chapter 4. Chemical foundations. Subtitle to chemical foundations is Elements, Atoms, and Ions. All right. So this is just an outline of what we're going to cover today. And so I'm just going to get started with it. So at one time, there were only 115 elements in the periodic table. When this original slide set was made, that's all there was. Now we have 118 elements in the periodic table, and every one of them has a name and a symbol. So when you fill out that extra credit, be sure to put the 2-letter symbol for each of the elements. All right. About 88 of them can be isolated in natural sources, and the rest of them are man-made. However, some of those that were originally man-made have since been isolated in nature. And the reason for that is that they are so rare and difficult to isolate that we didn't know they were out there in nature until just recently, when our analytical techniques had improved. So now we believe there are about 98 of them in natural sources, and the rest are man-made. All right. So the reason I want you to learn those chemical symbols is that that is the alphabet for chemistry. That's how you say what is happening when a chemical reaction occurs. You use those symbols. That's how you identify an element, a compound. And that's the language of chemistry based upon those symbols. So if you don't know those symbols, then you'll be lost for the rest of the semester. Okay, here's what that periodic table looks like, and the ones that I want you to memorize. You can see that around some of them are these red boxes, like hydrogen, H for hydrogen, or He for helium. That's a mistake. And I'll tell you why in just a second. First of all, not every one of them has a red box around it. Those you don't have to memorize. Right? So if you count up the ones that have red boxes around them, there should be about half of 118, maybe a little more than half. But those are the ones that are the most important, the most commonly seen in chemical reactions, and you need to memorize them. Now, about the blue background, the blue highlight for the elements. Those elements in blue highlight, when a problem or question is asked and it references, say, for instance, hydrogen reacts with oxygen to produce water. Hydrogen, oxygen, water. When you read that problem, you need to know that hydrogen is not the single atom in this reaction. It's always diatomic, and so is oxygen. If you don't know that, and you try to write the chemical reaction, it will be wrong. And it will never balance. We haven't got there yet, but trust me, it will not balance. Okay, here's the problem with that periodic table. Notice that blue box around helium. Helium, that's an error. Helium is a noble gas. Noble gases do not bond with anything, not even each other. So that blue box should not be there. The other blue boxes, yes, those elements are diatomic. So hydrogen is diatomic, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those are all diatomic elements. When you read them in a word problem and it says iodine reacts with something, you better write it I subscript 2. All right. So how do you memorize the symbols? The best way I found for most of my students is to get you some 3x5 index cards. On one side, write the name, the full name of the element. And on the other side, write its symbol. All right, we're going to talk about the symbols in just a minute. But once you get those cards written, you've already started memorizing it because you're writing it down yourself. And then you take those cards and you go through them one by one. You look at the element name and you say the symbol and look at it. Get it right, it goes in the right pile. Get it wrong, it goes in the wrong pile. And you keep doing that with the wrong pile until you get them all in the right pile, and you start over again. And you go through it, name to symbol, and then you go through it again, symbol to name, until you can do it without mistakes. That's how you memorize the symbols. All right. Just a word or two about elements. When we talk about an element, we mean a substance that cannot be divided or reduced any further. It cannot be divided into two unique substances or more, right, by physical means. Now, we can't separate the atoms of an element into two different types of atoms or more, 2 or 3 or 4 more types of atoms. It can't be done. When you separate those atoms, you always get the same types of atoms in your separation. That's an element. It is unique. It has unique physical and chemical properties. Now, this slide talks about the abundance. When we look at the distribution of the 18 most abundant elements in the Earth's crust and the oceans and the atmosphere. We're not going down deep in the Earth, just the crust, oceans, and atmosphere. What is their abundance? By mass percent. What do we mean by mass percent? Well, in case we didn't cover it before, mass percent is the mass of the element divided by the total mass of the sample times 100. Okay, that's all it means. So if we're looking at mass percent, the most abundant element in the Earth's crust, in the atmosphere, in the oceans is oxygen, right? And for good reason. When you consider that almost every element in the Earth's crust is some oxide, it's some combination of elements with oxygen. So oxygen's got its fingers in everybody's pies, most of the time. The other, in the oceans, the lakes and oceans, what's the most abundant compound is water, right? There you go. There's another massive source of oxygen in the oceans. How about the air we breathe? The air we breathe is 21% diatomic oxygen. So that's why oxygen is the most abundant by mass. Now, when we look at the second one and the third one, silicon and aluminum, and even iron, most of their abundance comes from the Earth's crust. Think about sand. Sand is almost pure silicon dioxide. Okay, there's your silicon. And most of the rocks and soils in the Earth's crust are combinations of silicon and aluminum and oxygen with some other elements interspersed. Like iron is one of them. It's very common. Calcium is very common. Sodium, potassium, magnesium, all very common. Hydrogen, however, has a very low mass concentration for one simple reason. There's lots of hydrogen, especially in the oceans, but hydrogen doesn't weigh very much per atom. So if you're looking at mass percent, hydrogen doesn't contribute very much mass. Now, there are lots of hydrogen atoms out there, but not very much mass. All right. So I gave you a definition of element before. You maintain the identity of the substance no matter how far you divide it physically. Separate atoms, separate atoms, separate. They're all the same, right? Chemically and physically. So their similarity could be attributed to a single atom, to 5 atoms, to 1,000 atoms to a billion atoms. All the atoms are identical chemically. So that is an element. It could be a single atom, or it could be one of these diatomics, right? Or we may be referring to the atoms of elements that are present in something. If we say the elemental composition of water is hydrogen and oxygen. All right. So you'll notice in the periodic table, the way the symbols are written for each element, they always have, the first letter is always capital. And if there's only one of them, that's where you stop. Hydrogen is capital H, that's it. If, on the other hand, we have other elements that need to have an H first, it is also capitalized. But the second letter is always a small letter. So for helium, it's big H, little e. All right. Let's see. There's another one. I don't think you have to memorize this one, but for illustration purposes, there's another one that starts with H, and its second letter is F. It stands for hafnium. It's a transition metal, which doesn't mean anything right now, but it will. They're always written this way. If you write an element that has two letters in it, if you write its symbol and you capitalize both of them, it is wrong. For instance, if you write this one, let's try, let me give you a different one to illustrate the point. If we want carbon, that's not a good one. Hold on a second. Okay. If I want to write the symbol for cobalt, this is the proper symbol for cobalt, big C, little o. If I write it like this, then anybody who knows anything about elemental symbols and compounds will think this is carbon and oxygen. This would be carbon monoxide, not cobalt. So that's where the misunderstanding can occur. If you don't write it correctly, then anybody looking at it is going to see it wrong. You meant to write cobalt, but instead you wrote carbon monoxide. That's a compound. This is an element. Okay, first letter is always capitalized, second letter is not. Examples: oxygen O, krypton, big K, little r. Now, many of the symbols can be traced to and memorized in terms of their English names. For instance, oxygen is O. That makes sense. Hydrogen is H. That makes sense. He, big H, little e, is helium. That makes sense based on the way we spell it. But there are some symbols in there that are not derived from English words. They're derived from Latin words. The Latin name of the element then is used to derive the symbol. Gold, for instance, is big A, little u, right? No resemblance to GOLD, because in Latin, gold is aurum. A-U-R-U-M. So we use A, little u, big capital A, little u, for the symbol for gold. Lead is big P, little b, because it's derived from the Latin word for lead, which is plumbum. I like that one. Plumbum in Latin means heavy. Okay, lead's heavy. And there are several others like that. If you come across a symbol when you start writing your cards out, and you write out the English name, and on the other side, you try to write the symbol, and you look at your periodic table or a list of the elements, then you're going to find that some of them don't match. Those are probably derived from Latin. All right, here's a list. The periodic table that is presented with the red boxes around it does not have the names of the compounds. Names of the elements, only the symbols. So you got to look them up, and they will be in your textbook. Whether you have a hard copy or electronic textbook, there will be a list similar to this one. Or you can go to the internet and find a periodic table that has both the symbols and the names together. That works also. All right. Now let's talk about the history of atoms. And let me look at my hard copy so I'll make this a coherent story. All right. John Dalton was an English scientist. Back then they called them natural philosophers. And they dabbled in lots of different things. Right? They didn't specialize so much as we do today. But Dalton proposed a theory for the physical world. Let's put it that way. Called it the atomic theory. And it was an attempt to explain why certain of the laws that had been developed over the years by other scientists could be explained. His atomic theory actually borrowed from the ancient Greeks. Some of the ancient Greek philosophers believed that all matter was composed of an elementary particle they called the atom. And they called it the atom because in Greek, tomos means to cut or divide. And the prefix a means not. Right? You've heard of people described as atonal. That is, they're tone deaf. Atonal. They can't tell tones. They don't hear differences in tones accurately. So we'll call them atonal. This is atone, not cut. So that's where Dalton's theory starts. The problem with the Greeks is they said that some of them said that everything is made of the same atom. Right? Well, now you've got to explain why all these different substances have different characteristics. Why are their identities different if they're made of the same stuff? Right? So they struggled with that one for quite a while. Dalton took that concept and he said, no, every element is made of an elementary particle called the atom, but the atom of one element is different than the atom of another element. Now, he just leapfrogged the problems that the ancient Greeks were having. Okay. Now, these are, I'm going to present some of the laws that Dalton's atomic theory was attempting to explain. Okay. Remember, in earlier chapters, we talked about the difference between a law and a theory. Right? A law simply says, under these specific conditions, this is what happens. It makes no attempt to explain why. Whereas theories are usually accompanied with a model of the system that you're trying to describe, and the theory attempts to explain why. So we're going to look at the laws first. In this case, and in many cases, laws come first, and then somebody has a bright idea about why the laws work, and their theory then allows them to manipulate the system a little more to try to get at the whys. So the first one we're going to look at is the law of conservation of mass. It was proposed by Antoine Lavoisier, which is a Frenchman, in 1773. Notice that's just a few years before the American Revolution. Well, as it turns out, during the Revolution, the states, the colonies, enlisted the help of the French crown, the King of France, who saw it as an opportunity to spend money on a foreign war and cause trouble for the British, who were the French enemies. The problem was they spent so much money helping the Americans that they bankrupted the treasury. So after the Americans successfully threw off British rule, then the French had to deal with their bankruptcy. Well, the way that all kings do is when they run out of money, they go to the people and tax them. So the way the tax system was set up in those days was, if you wanted to be a tax agent, you bought a contract from the king for a certain amount of money, and then you collected taxes for the people in your district. And when the king said, I want so much money, you give it to him. And everything else you keep for yourself. So that's why the taxmen have always been aided. That's been the way taxes are collected forever. So Lavoisier's problem, before I get to the law of conservation of mass, Lavoisier's problem developed when the French king got in trouble with the people. And the people said, well, if the Americans can do it, we can do it too. So they revolted. The French Revolution then ensued, and the French king was deposed, and they set up they had I can't remember what it's called, but they had like a Congress where they had supporters of the king and supporters of the revolution in the same room. And they were battling it out, saying, what do we do now? What laws do we pass, and who's going to suffer for it? Well, that went on for a little while, and those that sat to the right of the podium were the royalists, and those that sat to the left were the revolutionaries. So even today, those on the right are the conservatives, those on the left are the liberals and the leftists and the ones who want to tear things down. So as it turned out, to make a long story short, eventually that body was dissolved and a ruling council was set up, and soon after that was the Reign of Terror. And their chosen device of execution was the guillotine. So lots of people lost their heads. All you had to do was point your finger at somebody you didn't like, and pretty soon they were gone. Well, nobody liked Lavoisier because he was the tax collector, in addition to being a scientist. So he got hauled up, and pretty soon he lost his head. Okay, that was a long story to set up this law from Lavoisier. Conservation of mass. It just says that during a chemical reaction, matter is neither created nor destroyed. If you account for all the mass of the chemicals before the reaction, then you conduct the reaction and collect all of the products from the reaction. The masses before and after are exactly equal. Total mass before and after is equal. Mass of the reactants equals the mass of the products. Okay, that's law number one. The next law occurred some years later. Joseph Proust, that sounds French, but he's really British, proposed the law of conservation, the law of constant composition. Sometimes it's called definite proportions. All this says is that with any given compound, the composition by mass of that compound is the same, no matter where you get the compound, no matter how you produce the compound. The mass percent of every element in that compound is fixed. It's the same. So for instance, if we isolate water from the ocean, right? We just distill the water, purify the water, it will have a composition of mass of hydrogen, mass of oxygen. Also, if you say, we're going to say hydrogen plus oxygen yields water, right? So I need two of these and two of these. What Proust is saying with his constant composition is that this water is indistinguishable from that water. Doesn't matter where the water came from, the mass composition is always the same. All right. And they're the exact values. 8 grams of oxygen for every 1 gram of hydrogen. Carbon dioxide is another example. No matter where you get the carbon dioxide, whether it's coming out your tailpipe, or you take a brick of dry ice and let it evaporate and collect the carbon dioxide gas, analyze it, same thing, no difference. Okay. Then along came John Dalton. See, all this happened in the latter part of the 18th century. Now John Dalton has proposed this law. This is before he gets to his theory. He actually proposed a law governing the identities of compounds. He called it the law of multiple proportions, not constant composition or definite proportions. This is multiple proportions. So what he says is that when you have a binary compound made of 2 different elements, and they didn't know at this time why that was, right? We do now, and this illustration says that we know now that when you have nitrogen here and oxygen here in this group, then if you have X mass of nitrogen and Y mass of oxygen, so many grams, for that compound, and you say, okay, I've got another compound, it's also made of nitrogen and oxygen, but they're 2 different, right? They have different characteristics. We know they're different. If you compare them now, then if you compare this many grams of nitrogen, you're going to have twice as many grams of oxygen. And if we have another compound made out of those 2 elements, and we know it's different, It has different characteristics than any of the other two. And if we hold that same number of grams of nitrogen, now you're going to have 3 grams, 3 times as much of oxygen. So the law of multiple proportion says under these circumstances, the ratio of these to each other is whole number multiples. Okay. Let me wet my whistle. Now we come to Dalton's atomic theory. Now he's trying to explain why these laws that had been proven correct, why they were correct. It had been recognized, and Dalton just included this as a statement. Natural materials are mixtures of pure substances, right? And I think we identified pure substances as those things that cannot be broken down any further by physical means. So a pure substance could be an element, or it could be a compound. So pure water, pure substance. And there you go. Pure substances are either elements or compounds. If they're not, if you have 2 or more pure substances mixed together, you have a mixture. And each of those pure substances retains its identity. Any given compound always contains the same proportion by mass of the elements. This is a restatement of Proust's definite proportions, definite composition. It's fixed composition. Okay. Now that was just a restatement of things that we knew up to this point. Now we get to Dalton's atomic theory. This is what he's saying is the reason for all of those laws being correct. Okay. And we've covered this one already. All elements are made of tiny particles called atoms. Right? He took that one from the ancient Greeks. But here's where he deviates. All atoms of a given element are identical. And all atoms of a given element are different than the atoms of another element. Okay. Now here's where he's starting to explain the nature of a chemical reaction. Starts off by atoms of one element can combine with atoms of other elements to form compounds. Okay. A given compound always has the same relative numbers and types of atoms. Okay, that explains the constant composition, right? They always have the same number of the elements in the compound, right? And it explains his law of multiple proportions, because all you have to do is combine different numbers of one element with the fixed element, say 1 oxygen with a nitrogen, 2 oxygen with nitrogen, 3 oxygens with a nitrogen, or even 2 nitrogens with 1 oxygen. And the law of multiple proportions now is explained. This is why it is. He also said, during a chemical reaction, the atoms of individual elements are preserved. You cannot change the atom of one element into the atom of a different element. during a chemical reaction. This also adds support to Lavoisier's claim, his law of conservation of mass. Because if you have the same number of atoms on this side, reactants, as you do on the other side of each element, then the masses are going to be constant. If you convert one element into another element, then the mass is going to change, right? And then the law will fall apart. So 5 is essential to understanding Lavoisier's law. He also said that during a chemical reaction, if you've got the same elements, but now with the chemical reaction, you have different substances as a result. The explanation for that is the atoms just rearrange themselves. They make different compounds by rearranging. They just swap partners. Okay. Now, what this slide attempts to do is to get us in touch with reality. When Dalton proposed the atomic theory, all of those statements were believed to be correct. And they explained everything that had been observed up to that point. But nowadays, we have made other observations and we have other information that Dalton didn't have. So now we're going to look at his statements and see which ones are still true. Okay. Elements are made of tiny particles called atoms. Is that still true? Yep, it's still true. All atoms of a given element are identical. Chemically speaking, yes. But physically speaking, no. And the reason they're different is now we know about isotopes. We'll have to talk about that in just a minute. A given compound always has the same relative numbers and types of atoms. That is still true. Atoms are indestructible. Now, we didn't give that as a statement in Dalton's atomic theory, but it's implicit in his theory. You can't destroy them. You cannot change one element into another during a chemical reaction. So this is another way of saying that they're indestructible. But we know that's not true either. Right? So that one's still true, and that one's still true, but Roman numeral 2 and Roman numeral 4 are no longer true. Let me see. Hold on just a second. I'm wondering, did we talk about hold on a second. Yeah, hold on. Well, I am going to explain in just a minute. Some of these slides, they might be a little out of order. Once we learn the symbols, now we know we can write formulas for the compounds with the arrangement, the different arrangements of the atoms in a compound. Okay? So each compound is a substance with a unique identity. So during a chemical reaction, you may end up with different substances. And the reason for that is the compound or the element. The element is either pure substance or you have a compound with multiple elements in it. That's how we account for the difference in substances that the Greeks could not. The formula, on the other hand, is based upon how we write symbols. Now, I can't recall if I've given you this before, but I'm going to do it now. When you write a chemical symbol, and I probably have a slide on this, but now is a good time to talk about it. There are 4 positions around that symbol, right? X is just stand in for whatever symbol. This position is the number of atoms. Okay. So if we have a diatomic hydrogen, it's H sub 2. 2 hydrogen atoms together in that formula. If we are describing an ion, one with a charge, that's where this goes. Charge is always placed up there. If we are describing other things about this element, such as the number of protons, that goes in this position. Number of protons, or the atomic number. And then this one is the mass number, which is equal to the number of protons plus the number of neutrons. Okay, those positions around the symbol are reserved for that information. Okay, so when we write a chemical formula now, we know that we're going to be using subscripts to say how many atoms are in that formula. In this case, we have SO3. SO3. How many atoms of sulfur are in that compound? Just 1. We never write 1 as a subscript. The reason? It's redundant. If you've got the symbol there, there's got to be at least 1 atom. Now, oxygen, we need a 3 because there are 3 oxygen atoms. Okay. You have to have the symbol, and you have to say how many atoms are in the formula. Okay. So let's take an example. Way back when I was a kid growing up, there was this chemical that had been developed, I think during World War II. Well, at least it was used a lot. And it was used into the late 40s, into the 50s, until the environmentalists got hold of it. And they said, you can't use it anymore. It's DDT. And this compound was identified as working its way through the food chain. If you used it, then small critters would eat stuff and pick it up, and then critters would eat them, and it was called trophic amplification. And the trophic, as you eat, you concentrate more and more of the chemical in your system. So the higher you are up the food chain, the more concentrated the material becomes. Now, DDT itself is not particularly hazardous, but it does break down into another compound called DDE. And that was found to cause problems, particularly with nesting birds. It would weaken the shells of the birds. And when they go to roost, they would crack the egg and destroy the embryo. So it was done away with. The point of this slide is, how would we write DDT? If we know that we have 14 carbon atoms, there's carbon, we have 14 of them, and we have 9 hydrogen atoms, and we have 5 chlorines. There's chlorine. So that's the molecular formula for DDT. Now, when they banned DDT, there was nothing that was quite as effective as DDT as an insecticide. So it was more difficult to delouse people. It was more difficult to destroy disease-carrying insects like mosquitoes. So the incidence of malaria, the incidence of yellow fever, all skyrocketed because you couldn't use it anymore. And there's no telling how many people died because the environmentalists took it off the market. All right. How about the structure of the atom? Okay. This goes back to the law, those principles of Dalton's theory that we determined were wrong. The atom is made up of subatomic particles. So in fact, it's still called an atom, but we know that it can be cut. We can break the atom apart. Not in a chemical reaction, but physically speaking, the atoms are made up of different particles. Now, why do we even care, right? Right? If we can't break them apart in a chemical reaction, why does it matter? Well, as it turns out, understanding how the atom is built provides enormous amounts of information, useful information, for predicting the behavior of atoms in chemical reactions. So we're going to start with J.J. Thomson. J.J. Thomson, at the turn of the 20th century, postulated the existence of electrons. And he knew that electrons originated in the atom, right? But they weren't atoms. They were a lot smaller than atoms. And they had a charge. And we knew that atoms were, for the most part, neutral, right? So this electric charge was a negative charge. And it had been, there were advancements in the sciences, and we could tell the difference between negative charges and positive charges. So J.J. Thomson used electrons that were emitted in a cathode ray tube and used that as his basis for experimentation. And obviously, since the electrons, which later named electrons, were coming from the atom, then there must also be some positive charges in there too, right? In order to balance the charges, the same number of positives as negatives would balance the atom so it would be neutral. And this is a reconstruction of the cathode ray tube that J.J. Thomson used. And it was simply a glass tube that had been evacuated, right? And it had 2 electrodes on it, and all you needed to do was apply a large enough potential difference, a voltage difference between these 2 plates, and you would get a stream of negative particles flowing through that tube. Sometimes you would have a very small amount of, say, a noble gas in there, very, very, very low pressure, just so that when an electron struck it, it would emit some light. You could see it, so you could see the beam. And then when you did that, you could play with it. You could apply 2 electrodes, a negative electrode on one side and a positive on the other, and see that the beam bend. That's how it was determined that the beam was charged particles. But you could also put it in a magnetic field and the beam would also bend. So what J.J. Thomson proposed was referred to later as the plum pudding model. If you've ever had a plum pudding, you know that in the pudding, you have this mass, and inside are pieces of plums. So what Thomson was saying was, in this model, the electrons are the plums, and the positive charge is scattered throughout that pudding. Okay? Let's see. We're not really sure who's responsible for the model. It could have been Lord Kelvin, whose last name was also Thomson, or it could have been J.J. Thomson that did it. We don't know for sure. But it persisted for a while. And there it is in black and white. What J.J. Thomson was able to do was determine the ratio of charge to mass for an electron. Okay, that's all he was able to do, just determine the ratio. So along came Robert Millikan. J.J. Thomson was an Englishman. Robert Millikan was an American citizen. He worked in the U.S. And just a few years after Thomson, Millikan determined that he wanted to find out exactly what is the mass of an electron. So he devised an experiment, and he built the equipment that was needed to conduct the experiment. It's famously called the Millikan's oil drop experiment. And the device he used put negative charges on very fine oil droplets and then suspended them between two electrical plates. And by using the laws of acceleration, the laws of gravity, and the laws of electrostatics with his plates, he could determine the mass of that droplet and the charge on the droplet. So he did this thousands of times. And what he determined was that each droplet had varying charges, right? But when he looked at them really closely, each of the data points for the charges on the droplet said that the charge varied by a certain amount. And it's always a whole number multiple. So he worked his way back to the simplest whole number, taking into account the mass of the droplet and subtracting that out. He was able to determine the mass of a single electron. And this is what it turned out to be. 9.11 times 10 to the minus 31 kilograms, right? Remember, kilogram is our fundamental unit of mass. And it's 10 to the minus 31. Actually, this is almost 10. So it's closer to 10 to the minus 30 kilograms. And he received a Nobel Prize in physics for his work in 1923. Excuse me, no. That was part of the Nobel Prize he received. He also did some other experimental work and confirmed Albert Einstein's photoelectric effect equation, for which he received the Nobel Prize. I believe that was in 1921. So Albert Einstein's work was theoretical, mathematical in nature. And Millikan provided the physical evidence that proved Einstein was right. Okay, so now we have a mass on an electron, and we have the total mass of the atom on average. The problem is the mass of the atom cannot be accounted for in any small way by the mass of the electron. So the positive charge must be huge mass by comparison. In fact, we determined it's about 1,800 times the mass of the electron is that positive charge. Well, Ernst Rutherford, who was an Englishman, just a few years later, took that evidence and he said, this plum pudding model is crazy. He didn't believe it. And he set out to prove that it was wrong. Well, if you do that, you've got to come up with a substitute. You can't just knock down buildings. You got to build something up too. So his proposal was the nuclear atom. Right? Rutherford said that his model of the atom had a very dense center, very small, dense center to it that was positively charged. That's where the positive charges resided. And most of the mass of the atom is there. And out here, in the rest of the volume occupied by the atom, are the negative charges. Right? So he set about devising an experiment that would differentiate between the plum pudding model or the nuclear atom model. Which one would win? Okay. So what Rutherford devised was what we call now the gold foil experiment. And here's the device. By this time, there had been considerable research on radioactivity. And several forms of radiation had been identified. The alpha radiation, and all of these forms of radiation originate from the nucleus that had been established and were produced by nuclear decay. They didn't know that the atom was decaying. Let's put it that way. They didn't know about the nucleus yet. The atom was decaying and giving off these particles. It was determined that the alpha particle is actually a helium atom with a 2+ charge. In other words, it has no electrons. It's just positively charged. The beta particle was identified and compared to electrons and found to be exactly the same as an electron. Okay, only it's moving at very high speed. So it's got the mass of an electron. This has the mass essentially of a helium atom. So it's much, much heavier than this. About 3,600 times the mass here of this. Right? And the other form was gamma rays. And this is light. So Rutherford said, I need something really massive, something heavy to fire at my target. So he picked the alpha particle because it's pretty big. And he said, when that happens, if I fire the alpha particle at this gold foil, if the plum pudding model is accurate and the mass of the atom is diffuse throughout like a plum pudding, a big bag of jelly, then the beam is going to go straight through and hit the other side. And all of these around here, all this is detectors, right? So you can detect where the deflection goes, if any, right? Plum pudding model says it all goes straight through. There's nothing massive enough in there to slow it down because the mass is diffuse. Said, my model says that the mass is concentrated in a nucleus. And if I fire alpha particles at my model, we will get deflections. Most of them will go straight through because the vast majority of the space occupied by an atom is virtually empty with just electrons out there. And they're not going to slow down an alpha particle at all. They might deflect it a little bit because the differences in charges. But most of them are going to end up over here, but a few of them will strike the nucleus. Sometimes they'll hit a glancing blow, right? Sometimes they'll hit head on and come straight back. And that's when Rutherford did the experiment. That's exactly what he found, was this. So Rutherford's model was the accurate one, and the plum pudding model from this time forward was dead. Okay, So now, now that we know about the nuclear atom, the positive charges are in the nucleus, the negative charges are out here in this space. Okay. All right. And there's kind of an animation of it. Now, why did Rutherford use gold foil? Well, he knew that if the target was too thick, nothing was getting through. He needed something really thin, like just a few atoms thick. And he knew that gold could be hammered into very thin sheets, probably thinner than any other material. So, and it didn't take much, just a very small piece of gold. So even in those days, even a poor research scientist could afford to buy a little piece of gold or have it donated. All right. So there's another way of looking at it, right? Most of the atoms pass through the gold. Some of them bounce off the nucleus. Okay, that's enough of that. So here's just a summary of everything we've covered so far. Dalton's atomic theory, to explain all the previous laws. Then we come to discovering what actually makes up an atom, because an atom is not indestructible. It's made up of pieces. Rutherford's nuclear atom was pretty much it until the latter part of the 20th century. And then I might add, it's not here, but I might add that Rutherford had a graduate student who, after his graduation, became a research associate with Rutherford for a while. His name was Chadwick. And the problem was that Rutherford's model was correct, but the total mass of the atom could not be accounted for by just the protons. They couldn't account for the total mass, so there had to be another particle in the nucleus that was about the same mass as the proton, but with no charge, because they'd already accounted for all the charges with the protons and electrons. That neutrality part. So the Chadwick set about identifying the neutron, which we abbreviate like that. And Rutherford got a Nobel Prize for his work. Chadwick got a Nobel Prize for his work. And now, with subsequent research and theories that developed, we have the modern concept of an atom. The modern concept of the atom. The nucleus is composed of protons and neutrons. And all the electrons are outside the nucleus. But the electrons, sometimes they behave as particles, sometimes they behave as waves. And most of the time, if you want to know anything about what's happening with an atom, the energy of its electrons in particular, you can't treat them as particles. They have to be treated as waves. So the modern concept of the atom treats electrons as energy waves. And they occupy, we're talking about probability now. They occupy regions of space with different shapes, different directions that they point, and these we generally call orbitals. These are where the electrons reside. But it'll take too long to describe that. You'd have to take my general chemistry course to get a more detailed explanation. Okay, so there's our down through the ages And this is a summary of research that is done over the years. Not everybody. Dalton, Thomson, Rutherford. Then along comes Niels Bohr. Niels Bohr proposed the planetary model, where the electrons were treated as particles. And they had their positions outside the atom, and the higher they were, the further away, the higher the energy. It was a planetary model. And it only worked for hydrogen. Along came Erwin Schrödinger, who was a physicist and a brilliant mathematician. And he was instrumental in proposing the quantum mechanical model for the atom. He wasn't the only one, but he developed a series of equations that could be used to predict the energies of electrons around the atom. We're not going to go into a lot of detail with him. Okay. Oh, here's Chadwick. Like I said, the neutron is not charged, but it has about the same mass as a proton, just a hair more. Okay, so the atom contains electrons, protons, and neutrons. Okay, the nucleus is very small, but extremely dense. And there's the relative masses. If we set the mass of electron at 1, then the proton is 836 times as massive, and the neutron is 839 times as massive. So the question now arises, how do we explain the difference in chemical properties of the different atoms, the different elements? When you think of chemical properties, how do we know that a given element has a property? We have to compare it to something, right? You got to bring something close to it to react with it, to see how it behaves. And you may have to bring several other types of elements close to it and see how they react. Okay? So on the atomic level, what's happening? When two atoms approach each other, what do they see first? They see electrons, all these electrons out here. So the nature of chemistry is with the interaction of electrons and the orbitals that they occupy. Okay? That's where the chemistry happens. And that's why we need to know something about the structure of the atom in order to make predictions. Okay. It's the number of electrons that are available to react and where are they located. That determines the chemical properties of an element. Now, this topic, isotopes, this is where we blow Dalton, one of Dalton's postulates out of the water, because he said that all atoms of a single element are identical. Well, chemically speaking, yeah, they are. But they're not all identical, because now we know that the nucleus is made up of protons and neutrons. If we know the number of protons, then we know which element it is. That is an identity for the element. So if you know it's got 6 protons in its nucleus, it has to be carbon. It can't be anything else. If it has 7 protons in its nucleus, it's nitrogen. If it has 8 protons in its nucleus, it's oxygen. You cannot change the number of protons without changing the element. But you can change the number of neutrons, right? And you still got the same element. but it's a different mass. So same number of protons, but different number of neutrons, that's an isotope of that element. And all naturally occurring elements have 2 or more isotopes. Okay. Now, for the most part, naturally occurring abundance of isotopes for a given element are heavily weighted toward 1. And the second, third, fourth, fifth, however many there are, they're minor components. There are a couple of exceptions, right? Chlorine is one. Chlorine is a mixture almost 50-50 of 2 different isotopes. Majority isotopes. It has a whole bunch of isotopes, as most of them do. But they contain mixtures of isotopes. For instance, if we write sodium up here using our convention, it has 11 protons, right? If it doesn't have 11 protons, it's not sodium. But how many neutrons does it have? If it has 12 neutrons, then the mass number is 23. Right? Remember, number of protons plus the number of neutrons. So how many neutrons does it have? Subtract 11 from 23, and you have 12 neutrons. How about the other one? Say this one is 24, mass number. That means we have 13 neutrons. Okay? These are different isotopes. Now, their chemical behavior is very close. Very close. But it's not identical. There will be a small difference in chemical behavior. It's still so small, it's very difficult to separate the isotopes by chemical means. It can be done, but it's difficult. All right. So this is the slide that I stole my own thunder earlier and gave you the symbol with those atomic number and mass number positions occupied. Okay. So there's another example. Carbon-14. Everybody knows about carbon dating. Anything that was ever living, and it's not too old, I'd say less than 10,000 years old, then it can be dated using carbon-14 dating. Carbon-14 is radioactive. This isotope will decay over time. And if you measure the ratio of what carbon-14 is left and what it turns into, then you can postulate the age of that material that has been fossilized. Right? There's the symbol. There's the number of protons. There's the mass number. So that means it has 8 neutrons. Carbon-12, on the other hand, only has 6 neutrons. Okay? But it still has 6 protons, right? They're joined at the hip. Number of protons, element. You can't have one different from the other. If you have 16 protons, you've got sulfur. All right. Suppose, and I'm running short of time. Let me check my. All right. Officially, I've got another 30 minutes, but it may take a little longer than that. Let me see how much more I've got to do. Yeah, a little bit. So let's spend some time on this because it's important. So if we have an isotope of this element, it has 23 protons. and it has 28 neutrons. So if it has 28 neutrons, its mass number is 51. Correct? So the question, this is the given information. What's the question? Question is, what's the mass number first? We did that. It's 51. What's the element? Right. If you know the number of protons, you can find the element on the periodic table. You just go top to bottom, left to right. Gets bigger and bigger and bigger and bigger. So we follow it down till we find 23 on the periodic table. And we find that this is actually vanadium. Okay? Simple. All right. Now let's talk about the periodic table. Okay. We're going to be using the periodic table a lot. So we need to know how it's constructed. It didn't just fall together out of the sky, right? It's a logical arrangement of elements to rationally organize them so that they have groups with similar properties and periods that I'll have to explain in just a minute. But the first periodic table was devised by Mendeleev. He was a Russian. And this is his first publication. Of course, see, it's in Russian. Can't read that, but we do recognize the symbols, right? All these symbols. Notice that occasionally there are missing ones. There's a question mark there. There's a question mark. There's a question mark. There's a question mark. Here's a question mark. Question mark. Okay. When Mendeleev put his table together, nobody knew anything or how to arrange in terms of atomic numbers, numbers of protons. They only knew masses. They knew relative masses of the elements. So Mendeleev organized them by relative masses and by similar chemical properties. He put them in families. Well, if you put them in order and you say, okay, this one's got a certain characteristic, the next one has a different characteristic and it's more massive, and you put them in order. And then you come along and say, well, this element is heavier, but it has a similar chemical behavior to the one above it. Okay, fine. Now you're down in another row. This one, the next one is heavier, but it doesn't have the same chemical properties as the one next to the one above it. That, okay, don't put them in there. They're not in the same family. Move it over to this one where it does have similar. So there's a hole left. That's the way Mendeleev put his table together, and that's what those question marks are for. He said, we don't know, we have not isolated all possible elements in nature. And this hole that I left in here is one day going to be occupied by an element that someone's going to discover, and it will have this mass, and it will have these chemical characteristics similar to the ones in that same family. And sure enough, every one that he predicted was discovered and had similar masses and properties to the ones that he put in those families. So that's why Mendeleev is considered the father of the periodic table, because he used it to predict. Whereas everybody else that was working on relative positioning of elements didn't do that. They didn't bother. Mendeleev did. Now this one, the families are left to right. But in his second publication, he rotated his table 90 degrees and put the families in vertical groups. And let's see. Yeah, This is his second table. So this group, these all have similar properties. These have similar properties, similar properties, similar properties, all the way down. And notice it, he's got some that are still missing, I think. Let's see. Well, yeah, these are positions here that are missing elements. Now we have the modern construction of the periodic table. And you'll notice that in this version of the periodic table, we have some elements down here that don't have two-letter symbols. These symbols here are placeholders. We now have two-letter symbols for all of those elements. So every element in the periodic table has a name and a symbol associated with it, all the way up to the biggest one we know, 118 atomic number. But the families, similar properties are grouped in vertical groups. Now we call them groups instead of families. And from left to right are periods. Okay. Now, why do we call them periods? I think it goes back to the concept of periodic motion in physics. What's periodic motion? Well, everybody understands what motion is. Something moving, right? If your car is moving from here to there, it's linear motion until you turn a corner, of course. But periodic motion is motion which goes through a cycle and comes back to where it started. Think of a pendulum like that. So a period in the periodic table has these groups assigned elements, and when you follow them all the way across, say we go all the way here to argon, the next one next to argon will be potassium. But we don't need to start a new group. Potassium behaves like lithium and sodium, so we put it in this group. So we started down there and we circle back, right? The pendulum swung all the way back. Now we're there. That's periodic motion in the table. That's a period. And they're numbered. Period 1, 2, 3, 4, 5, 6, 7. And the groups are numbered also. The extra credit, I want you to number them in the modern scheme. And that is just 1 to 18 from left to right. So 1, 2, 3, 4, 5, 6, 7, all the way across to the other side. All right. And this arrangement also increases from left to right through a period and from top to bottom through the groups. So 1, 2 for helium, then 3, 4, 5, 6, 7, 8, 9, 10, and back around 11, 12, 13, 14, 15, all the way across. Now we're going to see at some point that there's a logic to the way these are arranged. I don't know how much detail that we're going to be able to expose, but you'll notice that in this period, when you get down to this period, you come over to lanthanum, 57 atomic number, and then there's a big break here, 57 to 72. In that gap goes this row right here. Those are called the lanthanides after this element. These are the lanthanides. And the reason we pull them out primarily is so that the table doesn't stretch to China. It's more compact. But these, all these go right in there. And all of these go right in here. These are the actinides, lanthanides, actinides. All right. It's an interesting story where the atomic number came from. Because when Mendeleev created his table, they didn't know about atomic numbers. He was ordering things by mass and similarities of properties. But there was a young chemist, English chemist, named was Henry Moseley. And he was doing research on primarily metals. And he was firing X-rays at them. And he was measuring the spectra, the emission spectra of elements as he fired X-rays at them. And he noticed that he could devise a formula. And in the formula, all he needed to do was change one variable. We call it X. Change that variable by one whole number increment. And he could accurately predict the wavelength of emission for the next element, right? If he changed it from 19 to 20, he knew that his formula would predict the wavelength, emission wavelength for this element. And then 21, do it for that one. So he called that his atomic number. And that atomic number, he didn't recognize it in the beginning, but it was identified with the number of protons. Now, unfortunately, Henry Moseley lived 1914, right? The beginning of World War I. Well, he finished his work and published his work on the atomic number in this research, but then he went off to war for his country and died. So that's the end of his research. Okay, so the periodic table is, we're going to talk about its structure now. We've talked about groups and periods. Now we're going to talk about general characteristics. We have the periodic table can be subdivided into metals and non-metals. We talked about groups and families already, and periods, right? Those are the horizontal rows. Families are the vertical columns. Notice that metals and non-metals are divided by a dark line right here, right? These are yellows, but there's a dark line behind it. It goes like this, under boron, above aluminum, and then down between aluminum and silicon, like that, just stair-step it like that. So if you start in the wrong place, you're going to end up with the wrong line, and you won't get credit for it in the extra credit. So pay attention to that. On the right-hand side of that black line are non-metals, and on the left-hand side are the metals. So most of the periodic table is composed of metals, and we have a general idea of what metals do, right? They conduct electricity, they conduct heat. If you shine them up good, they have a luster. Non-metals, and most of them are solids, except for one, mercury. Mercury is the only metal that's liquid at room temperature. So they're mostly solids, whereas the non-metals are dull. They could be liquid, gas, or solid. They are insulators. They don't conduct electricity. They don't conduct heat. And they're, like I said, they're brittle as opposed to metals, which are malleable and ductile. You can stretch them into a long wire. And in fact, pure iron, you can scratch it with your fingernail. There are a few that are right on that black line, on either side of that black line, that we call metalloids. It depends on their chemical environment as to whether they behave like a metal or they behave like a non-metal, chemical terms. So these are metalloids: silicon, germanium, arsenic, antimony, tellurium, polonium, astatine. Those are considered metalloids. Okay, so this is another view of the periodic table. Let's see, why did I put that one up there? Oh, okay. So everything in blue is metals. These are metals. These are metalloids here. Noble gases are in green, and non-metals are in amber. The metalloids, which are the metalloids, it kind of differs between different authors. You know, some think they are and some say they are. Hydrogen is kind of off by itself. Hydrogen is really not an alkaline metal. But for balance purposes, we put it over here instead of on that side. Hydrogen is unique. Okay. Most elements in their pure form are very reactive. That's why in nature, we don't find them in pure form. Some of them, yes, we do. The noble gases, of course, right? We find those in pure form. And some of the metals, called the noble metals, are found in pure form in nature. Gold, for instance, platinum, palladium, those are considered noble metals. And that's why you can go to California or Alaska and pan and get little gold flakes, because they don't combine with anything. Now, they're saying that silver is a noble metal, but I take issue there. Silver is very often combined with other elements. You can find silver nuggets, yes, that's true, but they're not as common as gold. And that's kind of strange because there's more silver on the planet than there is gold. Silver is usually combined with something else, but platinum, yes, is a noble metal. Noble gases. Okay, so these are your diatomic elements, and I pointed those out previously in the periodic table. They will be diatomic like this at 1 atmosphere pressure and room temperature. And these are some characteristics. This table is in, it may not be that number, but that table is in your textbook, right? In chapter 4. It could be 4.4 or 4.6, I don't know. This is an old slide set, so that could have changed over time. Now, it's a funny thing. Pure elements can exist in different forms themselves, right? And we know they're pure elements because they've been analyzed and they're only the atoms of that element in there. But they can have different characteristics based upon their arrangement. They can bond with one another. And that's where we get the idea behind allotropes. They're just different forms of the same element. Examples. The example I love the best is carbon. Carbon occurs in actually more than 3 forms. One of the most expensive kind is diamond. That's pure carbon, although sometimes it has some impurities impregnated in it. But a pure white diamond with no flaws in it is carbon atoms bound to each other. It's like a single molecule. If there are no flaws, then you could follow the carbon atoms in bonds between them from one side of the diamond to the other side. But it also occurs as graphite. That's another allotrope, right? And they're completely different, obviously. Diamond is the hardest material in the Mohs scale of hardness, number 10. And graphite is way down the list. I think the softest material on that scale is talc. And graphite's not far behind. And then there are fullerenes. Buckminster fullerene is one type, which is 60 carbons attached to one another in a ball. Sometimes they call them buckyballs. But there are also fullerenes that are tubular in shape. Those are nanotubes. Okay. So this is what they look like. There's the network solid, the diamond on the left. The graphite is hexagonal arrangements in plates. So the attachment between the plates is very weak, whereas the bonds between the carbon atoms in the plate, in the hexagonal structure, are very strong. So what you get is a lubricant, a dry lubricant. And I used to use graphite powder when I rode motorcycles. You just open up the cap on your cable, your brake cable or your clutch cable, and take that tube and squirt some graphite powder down in there, and it would lubricate the cable, but it was dry. It would not attract dust. There's a buckyball, and there's a nanotube. Notice the nanotube has this hexagonal structure. It's like graphite, only it's twisted around into a tube. Okay. Now, how do we form an ion? Right? A charged atom is an ion. It could be negatively charged, it could be positively charged. How do you form it? Well, you've got protons in there that are positively charged, right? In this case, magnesium. Right? Magnesium has 12 protons. It also has 12 electrons. If it's neutral, right? No charge up here. So how do you make an ion out of magnesium? Right? Do you change the number of protons? Right? If you add a proton to it, then you have 1 plus charge. Right? It would be out of balance. What's the problem with that? You change the number of protons, you don't have magnesium anymore. So the only way to make an ion is to change the number of electrons. If you add electrons, you get an imbalance toward the negative. If you subtract electrons, you get an imbalance toward the positive. That's how you make positive ions or negative ions for an atom. As it turns out, magnesium prefers to lose 2 electrons. So if it loses 2 electrons, now we have an excess of 2 positive charges. Right? And magnesium 2 plus is the most common ion for magnesium. If it forms an ion, it will be 2 plus. Now, by the way, how do you form those ions? Right? How do you get it to give up those 2 electrons? Well, you can do it with heat. Just add a lot of energy, and 2 of those electrons in the outermost region will just, they'll have so much energy, they're gone. Or you can put it in vicinity of another element that prefers to attract electrons rather than give them up. Magnesium wants to give up electrons. Say chlorine, a nonmetal, wants to attract electrons. Right? So if you put chlorine close to magnesium, then magnesium will give up its electrons to chlorine. Now chlorine has a negative charge because it has excess electrons, and magnesium has its positive charge. And if you do that, then they'll attract one another, right? Electrostatics, pure and simple. All right, that's how you make an ion. In this case, we've got chlorine. There's your chlorine. Right? Chlorine has 17 positive charges. Right? Has 17 protons and 17 electrons. But it wants another electron. It would rather be 18. So now it's a -1. And that's preferred for chlorine and all the elements in its family. Fluorine, chlorine, bromine, iodine, they each only want 1 electron. Magnesium wants to give up 2. Well, if the compounds are neutral, that is, compounds are not charged, then how do you get them to be neutral? You have to have the same number of positive and negative charges, correct? So if this magnesium has 2 positive charges and there's only 1 chlorine, you can't make a neutral compound with it. You need 2 of these, don't you? You need 2 negatives. So if we put 1 magnesium together and 2 chlorines together, we've balanced the charges, right? This is 2 plus, this is 1 minus, but 2 times 1 minus is 2 minuses. And 1 times 2 plus is 2 pluses. It's neutral again. All right. Now, when we have a positively charged plus or whatever number of positive charges, or we have another element with negative charges, these are called cations. And this one's called anion. Let's make it singular. That's a cation, that's an anion. Positively charged is cation, negatively charged is anion. So, let's see. I'm going to leave this off here. This suffix, don't bother yourself with it in this chapter. Chapter 5 is going to go into more detail, and we'll use that rule. So we're going to let that slide for now. We'll come back to it in chapter 5. Okay. Now, in the periodic table, certain groups prefer certain charges. Okay. So notice that we're using a different, this group is called 1A. That's the older system. 1A, 2A, 7A, 8A. Let's not linger on that right now. But the alkali metals are the first column to the left in the periodic table. Right? Lithium, sodium, potassium, rubidium. Those are in the same family, and they always prefer 1+ charge in a chemical reaction. When they form an ion, they prefer 1+ charge. The next column to the right is the alkaline earth metals, or alkaline earths for short. Beryllium, magnesium, calcium, strontium. They always prefer a 2+ charge. We go to the far right of the table, we find the noble gases. They don't like charges at all. Right? They're always neutral. Okay, that's why they don't react with any other elements, because they don't want electrons, they don't give up electrons. They do not react. Halogens, however, though, just to the left of the noble gases are the halogens. Fluorine, chlorine, bromine, iodine, astatine. In that family, they always prefer a 1- charge, like the chlorine we just showed you. And there are other groups. We'll get to those in a minute, I hope. Here we go. Here's a list of groups which give the preferred charge. We talked about the alkaline metals. These are the alkaline earths, right? +1, +2, -1. Those are the halogens. The next group over here, the oxygen group, they're called chalcogens. The oxygen group, they prefer a 2- charge. So oxygen, sulfur, selenium, tellurium, they're all 2- charge. The next group over under nitrogen are the pnictogens. The P is silent. Nitrogen has a 3- charge, phosphorus has a 3- charge. The boron group doesn't have a name, but boron, aluminum, gallium, indium, those are 3+ charge. It's important that you recognize those, and also that these charges are typical of the metal or the non-metal in a complete transfer of electrons, and a transfer that forms ions. There are some reactions that don't form ions. We haven't got there yet. But for naming purposes, it's important that you know these charges for those families, for those groups. These elements in here, the transition metals, right? And some of these over here, they tend to have multiple possible charges. You can't predict those unless you actually have the compound and its formula. Then you can deduce the charge. But they don't have a preferred charge like the single charges on these groups that are given there. Okay. All right, let's see how much we understand about forming ions. We have an ion with a 3+ charge. Okay. And it contains 23 electrons. All right. What ion is it? It's not that difficult. Look, 23 electrons, but it has an excess of 3 positive charges. Where do the positive charges come from? Protons. So it has 3 more protons than electrons. How many protons does it have? 26 protons. 26. Go to the periodic table. Look for atomic number 26. And we find out that it is Fe, iron. That's one of those Latin terms. The Latin word for iron is ferrum. And it has a 3+ charge. So there's your ion. All right. Okay. Let's try this one. A certain ion, X+, has a single positive charge, has 54 electrons, and 78 neutrons. All right. That's given information. Let's see what the question is. What is the mass number of this ion? How do we determine the mass number? We need to know number of neutrons and number of protons. So if we have 1 extra proton than electrons, that means we have 55 protons. And the mass number then would be 133. A, mass number equals 133. Okay. Which element is that? Doesn't ask that question, but I'm asking. Well, if it has 55 protons, looks like it's cesium. And cesium is in the alkali metal column, the very first one on the left. Those are all +1 charge. So that's your cesium. All right, moving along. So up to this point, we've been focused on compounds that are made of ions. So how do we get ions to behave like that? If you've got a certain amount of, say, let's see, yeah, we're using sodium and chlorine. Sodium is in the first column, chlorine's in a halogen. Sodium is +1, chlorine's -1. Only when they react, they're neutral when they're separate atoms. But when they react, sodium gives up an electron and chlorine accepts an electron. That's only if we're looking at one atom each. But when you've conducted the reaction with sodium metal and chlorine gas, you've got a whole lot more atoms of each behaving. So here's what you end up with. You end up with a crystal, right? If you've ever spilled salt on a table and looked at it with a magnifying glass, they're little cubes, little bitty cubes. They're composed of sodium ions and chloride ions in a matrix. So you would have this sodium would be surrounded by chlorines. Let's move this one over. And then there'd be one on the other side of the board and one on this side of the board, right? 6 of them around it. But each chlorine would also have a sodium around it. Okay, so you form what's called a crystal lattice. So why do we write the formula for sodium chloride like this? Because it just wouldn't make sense, and it would be really busy to say for every crystal of different sizes, you would have a different number here. Like you would have 10 to the third here and 10 to the third there. So what we do for ionic compounds is we write them with the simplest whole number ratio of cations to anions. And the simplest ratio, because these are equal, the simplest ratio is 1 to 1. And that is also based upon the charge. Because that's one positive charge, it's one negative charge. We only need one each to give the simplest whole number ratio. Okay, now how about properties of ionic compounds? Well, the forces that are holding these ions together are very strong. So they have extremely high melting points. In other words, they're locked in this crystal lattice, and the only way to get them apart, well, one of the ways to get them apart is to heat them up. Give them a lot of energy so where they start vibrating, they're shaking, and they shake themselves loose. And now they're a liquid so they can move past one another. They only conduct electricity when the ions are free to move. So melting is one way to get the ions free. And then a sodium chloride crystal, once melted, will conduct electricity because the charges can move and go from one electrode to the other, complete the circuit. The other way is to dissolve it in, say, water. Then the ions are free to move again. when you write an ionic compound, or when you isolate an ionic compound, it's always neutral. There's no electrostatic charge in a compound. You have to balance the charges for ionic compounds. Right? So our earlier example, magnesium chloride, you have to have 2 chlorines because they're only -1 each. But magnesium is an alkaline earth. It's in the second column, and they're all +2. So there's your formulas for the compound based upon balancing the charges. All right, so let's try this one. Right, I'm over time, but I'm recording this, so it's not an issue. If we have an unknown ion X bound with 2 chlorines, and the X contains 20 electrons. 20 electrons here. What's the identity of X? Well, if this formula is correct, and there's only 1 X for 2 chlorines, then the chlorine ions being -1 each gives us a -2 total. That means this 1 has to be a +2. And if it's a +2 and has 20 electrons, how many protons does it have? It has to have 2 extra protons, correct? In order to give you a 2+ charge. So this 22 means what? What's the identity of X? Well, we look at the periodic table and follow along till we find 22, and it turns out to be titanium. So the identity of titanium is actually this with a 2+ charge. Okay. All right, let's see what we got here. A member of the alkaline earth metal family. Alkaline earths, remember, are the second column from the left. Most stable ion contains 36 electrons. So this X has 36 electrons. It's an ion. So what do we know about alkaline earths? They prefer a 2+ charge. We're going to form a compound with this with bromine. So what's the charge on bromine? It's a halogen. Same as fluorine and chlorine. It's a -1. Okay. So, do we even need to know the number of electrons? Well, not to say how many these are, it has to be 2 to balance. But we want to know what X is. So if it's got 36 electrons and 2 extra positive charges, that means 38 protons. Right? So 38 gives us strontium. So this is strontium with a 2+ charge, and bromine, 2 of bromines right there. So when we write these compounds, we don't put the charges typically. This is just my bookkeeping scheme. So the compound will be written Br2. Okay. And that's it for chapter 4. So what we'll do is see, this is Thursday, next Tuesday. I'll be here. You can zoom in if you want. I'll be here and I'll cover chapter 5. And chapter 5 is going to be on nomenclature. How do you name compounds? And if at all possible, You need to have memorized those symbols. Because when we name a compound, we're working from a formula for a compound. And to write a formula, you got to know the symbols. And if you want to write the compound formula from the name, you got to know the symbols. Okay. So we're going to talk about nomenclature. We're going to talk about how to name compounds and how to write compounds from their names. That's on the agenda for next Tuesday.